Well, hello and welcome to the next in our series of spatial awareness hangouts. Today we're going to talk about comets again. I'm joined by two people. I'm joined by Alan Fitzsimmons, who's on top of a mountain in Chile. So, hello, Alan.
Hello.
So Alan's currently at the Very Large Telescope doing some observing, and we'll hear more about what he's doing there when he's finished his coffee. And I'm also joined by from Oxford, so not on top of a mountain, Becky Smethurst. Becky, welcome.
Hi.
We're going to chat about the Rosetta mission, ESA's Rosetta mission. It's Philae lander. I'm not sure whether I've got the pronunciation quite right there, but Philae seems to be how I've been pronouncing it anyway. Its encounter with Churyamov-Gerasimenko, the Comet's 67P, and points for pronouncing it, I guess. We'll talk a little bit about what it's going to find and what it's found so far. So, Alan, first of all, Rosetta's gone to this comet. Remind us what exactly Rosetta is trying to do when it gets there, or now it's there.
Well, what it's trying to do is two different things, but both linked. First of all, they're trying to decipher exactly what the comet is made of. So, how did it form? How has it evolved over time? And what we're getting back from the Rosetta is not just these fantastic images of the nucleus of the comet itself, but also we're getting the actual in situ measurements of the gases and material that the comet is releasing. So we're already getting these important measurements showing us how comets are put together and how they were formed 4.5 billion years ago. But the second part of the Rosetta mission is not just to see the comet as it is now, but how it changes as it goes around the sun, because we know that comets release material as they go around the sun. And the other important task of Rosetta is to see how that comet changes as it follows it in its orbit for over the coming year. So, guys, I'm just going to have to move here because there's some noise in the background. Okay.
Okay, sure. Well, Becky, you're currently showing an image, or I think it might have just gone. So there's an image up there of the of what a selfie, if you like, from Philae. Let me just mute Alan while he moves. A selfie from Philae showing the Rosetta spacecraft's solar panels and the comet in the background, which is quite an amazing selfie. Now, one of the things you mentioned that it had done is it's been testing the smell of a comet. It's been looking at the chemical composition of the comet. So,
it's got a mass spectrometer on board, which, I mean, basically what that does is it figures out what sort of chemicals that the comet is giving off. I don't know if you can see in that selfie image, you can see sort of a gaseous jet coming off the comet. And so what it's doing is it's figuring out, how heavy the molecules are that it's getting, and figuring out which element that is. So you can tell what's in the thing, and they've actually released all this data recently to say that they've found stuff like hydrogen sulfide in there, and ammonia, and sulfur dioxide, and hydrogen cyanide. And all these chemicals actually, they have a smell. So basically what it's doing is kind of smelling the comet right now. And if you think those 4 chemicals I just named, that would smell like rotten eggs, a horse stable, vinegar, and almonds, which I think is quite nice.
Excellent. Well, a horse stable, I'm not so
maybe not the rotten eggs either, but fantastic. Anyway.
Now, Alan, I think just warning you, I think you're muted at the moment, so you might have just unmute somehow. If I can unmute, there we go. You're unmuted.
That's it. Okay. Just coming back to what Becky said, to point out first of all that most, or if not all, of these molecules that the Rosina mass spectrometer on Rosetta has seen to date, we've seen those on previous comets. The important thing, we've only been able to detect them from Earth in the brightest comets we've seen, and we don't know if there's anything special about those bright comets. And so what Rosetta is doing is it's giving these very precise measurements for the first time at, if you like, a normal comet, one of the many hundreds of comets we see orbiting the Sun every year. And that's really one of the powerful things that Rosina is doing for us, the mass spectrometer on Rosetta.
Now, when you say bright comets, you mean the ones that are very bright from Earth. So that's the ones that either come very close or are just very active and have a very big shell. So we can see an example of activity on Churyamov-Gerasimenko there, the comet that Rosetta's orbiting. Is that just it? Is it these bright ones just the ones that are bright from Earth? That's what you mean, right?
That's right. What we're looking at is we're measuring most of these, or almost all of these molecules from Earth or from Earth-based orbiting telescopes, and that means to receive the emissions from those individual molecules in the coma of the atmosphere of the comet. It needs to be really bright. It needs to have a lot of that gas there, so that we can receive the emissions from those molecules. Rosetta doesn't have that problem. It's in the atmosphere. It's in the coma. It's only 10 kilometers from the nucleus. It actually sucks, if you like, these molecules in and measures them individually. It's fantastic.
Mm.
Excellent. Now we can see on the image that's on screen now these fantastic jets that appear to be coming from the comet. And we've seen a number of those here. Becky's very kindly highlighting those with the crosshair there. We've seen jets from comets before, but one of the big advantages we've got here is we can really study it in detail rather than just from a flyby.
Sorry, Chris, you broke up a little there, but can you repeat the question?
So we'll be able to see this from jets as the comet evolves as it goes around the sun. And what do you think we're going to see from? Well, the expectations, if we see the expectations, that will defeat the object of going there. But what do we expect to be able to tell from how these jets change over time?
Well, I mean, okay, so first of all, we know from Earth-based studies of the comet, when it was last going around the sun about 7 years ago, that there are 3 main active regions on the comet. There's one in the northern hemisphere of the comet, pretty near the north rotation pole, and in fact that seems to be the source of most of those jets you can see in that picture that Becky has put up. If I can illustrate it with this 3D model of the nucleus, so most of the activity at the moment is coming from this neck region between the 2 lobes here, although there is activity actually over most of the comet that has now been detected by the... in a few months' time, we know that as the comet changes its orientation relative to the sun, there's going to be another region of emission much nearer the equator that's going to switch on. At least that's what it did last time it went around the sun, as we could see this large amount of material coming from the equatorial region. And then probably in next spring or early summer, we'll finally get the southern hemisphere illuminated. That's the part of the comet we haven't actually seen yet from the cameras on board Rosetta. And we know there's also another major source of activity there, and that will switch on hopefully 2 or 3 months before the closest approach to the sun, so we'll get good views of that as well. So first of all, we're seeing how the activity changes over the nucleus from these wonderful, wonderful images from Rosetta. But also, of course, what Rosetta also wants to do is see how the surface itself changes, because that material, when it's ejected from the comet, doesn't come back. The comet is eroding itself away every time it goes around the sun. And we want to actually see how that erosion happens. Where are these jets coming from? And how does that change the actual surface structure of the nucleus?
And one thought is that the surface structure of the nucleus is such that that neck region could have been caused by this erosion from that specific region. So this may have formed as a vaguely ovoid blob of material and then been eroded away around the neck. And that's hopefully something that we'll find out from Rosetta and possibly the Philae lander, I suppose.
That's right. Well, I mean, certainly from Rosetta, I mean, we've seen, as you said, these large jets coming from this neck region. Now, when Rosetta was first approaching the nucleus, there was a lot of speculation whether or not this was a binary object that formed from two individual nuclei that had come together sometime in the dim and distant past, when it was still an object out in the Kuiper belt beyond Neptune. But now it really does look like this could be the comet actually eroding itself away in the middle from these jets of dust and released gases. So it could actually be carving itself, so splitting itself in two. And of course, we've seen many comets split up as they go around the sun. However, there's still a lot of material there. I don't think we should worry at the moment about Rosetta having to orbit two nuclei rather than one.
This has been there for millions of years, right? So it's got quite a long time to go before it splits up. One would hope, if that is what's going to happen.
No, not millions of years. I mean, certainly the comets existed for millions or billions of years, but the average lifetime of a nucleus, even one as large as 67P, is measured in hundreds of thousands of years only. And in fact, we know in recent times that the comet's orbit has been changed by Jupiter. So it was back in the late 1950s that it actually ended up in its current orbit. Before then, it came in within 2 astronomical units of the Sun. So it only came in twice as distant from the Sun as the Earth is, and so then it would have been much less active. Before then, back in the 1860s, it was thrown in to that orbit from a much more distant orbit by the planet Jupiter. So it could be we're seeing actually a very fresh nucleus that's undergoing rapid changes at the moment. But this is something we don't really know to be certain, and we're hoping that Rosetta's going to give us some clues as to exactly how fast is this eroding at the moment, and how does that erosion happen? Does it happen all over the surface, or is it, as it seems to be at the moment, concentrated just in these areas of dust and gas jets?
Now, one thing that Rosetta carries on board is the Philae lander, of course. This little, I think it's described as the size of a small fridge. It's all space household appliances. This is going to land on one particular spot on the comet. So we have an image here of where it's going to land, and it's somewhere on the duck's head. Alan, on your model, could you help us identify exactly where the Philae lander is going to land in the model?
Okay, yes. So on November the 12th, I think it's about 8 or 8:30 in the morning, our time, Rosetta will aim itself towards the comet, release the lander, and then fire its thrusters again to make sure it doesn't go to follow the lander in towards the comet, but continues in orbit about it. And the lander would then take 7 hours to land onto the head of the comet just here. Now, the important thing to remember is that the nucleus itself is rotating once every roughly 12 hours, 20 minutes. So the lander is released here, and then it comes down as the nucleus rotates underneath it. So it's actually some pretty nice astronavigation to get it exactly where we want it. Now, it's not precise, it's not controlled. This is just falling under gravity. So once Rosetta lets go, there's no real control of the trajectory.
What I love about it is it's going to be falling at... is Alan still speaking?
I think there's a bit of lag there. So.
Okay. What I love about it is it's going to be falling at about 1 meter per second is the speed it's going to fall. And the escape velocity from the comet is 1 meter per second as well. So when it lands, it has to fire a harpoon to keep itself in place so that it doesn't bounce off the surface, which I think is great. I mean, who doesn't love a harpoon?
Yeah, indeed. Yeah, it's going to be great fun. Sorry, Alan, I think we sort of lost you a little bit there towards the end of your explanation. There's a little bit of lag. You went a bit quiet. Well, one of the things with Philae is that it's obviously only going to sample one bit of the comet, but what is it going to tell us about that one bit of the comet it lands on, and how can we extrapolate that to the whole surface of the comet? Oh, Alan's saying two. Oh, why Alan's saying two?
It's got two harpoons.
Okay.
It's got 3 screws in the three screws, one in each leg to screw it down, and it's got a little thruster on the top to try to keep it down. Because the one important thing is that Philae will land on the comet. We just don't want it to bounce.
Okay, so it will that helps it it stick into the surface, which is great.
So you broke up a little there. I guess the Wi-Fi connections here on the mountaintop aren't all what they're cracked up to be.
Well, one thing it would be good to know, since you're there, Alan, is you're there observing this comet for the purpose of aiding the Rosetta mission. You're up there at one of the largest telescopes in the world. What are you doing there up at the Very Large Telescope?
Okay. Well, first of all, I'm enjoying the view. Let me show you the view, if I can make sure it doesn't break up so much. So, here's the thriving metropolis that is the Atacama Desert, and as you can see, it's there's not a lot of life up here. In fact, we see very few animals up here because there aren't any plants. But if I swing around, so right now I'm in the astronomer's residence where we sleep and eat and do our preparatory work. If I swing around, you may be able to see just in the distance. It's about I think it's where is it? It's 2 or 3 kilometers away, just up on the mountain there. That's the Very Large Telescope, the 4 8.2 meter telescopes that make up the VLT. And the question is, let me just move it back here. Why am I here? I'm here because although Rosetta is making all these fantastic measurements, there's 2 things it can't do. There's so much it can do. It's probably right to say there's only 2 things it can't do. The first is that it's really close to the nucleus. It's at the moment within 10 kilometers of the nucleus. During the initial landing operations phase, it remained between 20 and 30 kilometers from the nucleus. And now from Earth, that's really close. It's in the same pixel on our images of the comet as seen from the Very Large Telescope. But that means what Rosetta can't see is what happens to all the material after it leaves the vicinity of the nucleus. So in our images on Earth, we can see the dust tail and the dust coma stretching behind the comet, something that Rosetta can't see. But also importantly, what we're trying to do, the reason I'm here is not to get images, so I'll be taking a few of the comet, but I'm taking spectra. I'm doing spectroscopy of the comet. Because we know, we've already heard from Becky, that the mass spectrometer on board has measured all these molecules in the near nucleus region. What we're trying to do is detect some of those molecules or their relatives much further out, so that we can actually see what happens to those gases, and of course the dust grains and the dust tail as well, after it leaves the vicinity of the nucleus and Rosetta. So that's the first thing. We're getting a kind of a wider but much lower resolution picture of the comet from Earth. The second thing is just as important, though, is that 67P Churyamov-Gerasimenko is only one comet. And we've studied hundreds of comets, some in great detail over the previous decades, even centuries. And what we want to do is we want to take everything we learn from Rosetta and try to apply it to this huge body of cometary knowledge we have. So if we observe Rosetta's comet the same way we've observed all the other comets, certainly in recent years or recent decades, then we can hopefully link in Rosetta's measurements to the measurements we make on Earth of that comet, and thereby to all the other comets as well. So these observations are kind of acting as this link between Rosetta's fantastically detailed investigation of one comet and all the information we've got about all these other hundreds of other comets that we've observed in the Earth's skies.
So it's important to get that global view. Now, there's a question coming. So Matthew Withers has asked, what's the surface made of? Now, previously, the only way we've been able to measure that is by looking at what comes off the surface. So you mentioned earlier, all the things that that Rosetta has seen have been the stuff that's come off the surface in the form of these jets and that form the tail. Philae is obviously going to get down to the surface and actually touch the surface of the comet. How is it going to? How is that? Well, it's obviously going to be able to tell us a lot more about it. But how is it going to tell us what the surface is made of? What does it bring to the table, as it were, that we can't do before?
Well, the problem is that from Earth we get a very, very coarse picture of what the surface of the comet is. We know it's dark. We know it only reflects roughly 5% of the light that hits it. We knew that from Earth-based studies. We also know from Earth-based studies it's kind of slightly pinkish or reddish. It reflects more red light than blue light, and that's about it. All that tells us is that the surface itself is covered in this cometary dust, the dust particles that haven't reached escape velocity from the nucleus, these small solid particles, and they're falling back onto the surface and covered most of it. But we don't exactly know what those dust particles are like. We've brought some of them back from Earth with the Stardust mission. We've observed them with ground-based and Earth and space-based telescopes, but we really don't know how this material works on the surface of the nucleus. How does it choke off all the material underneath? Because we know that comets are probably at least 50% ice, and so how does all of that ice sublimating? How does it clump together? We've already seen in the OSIRIS images amazing boulders boulders probably the size of the VLT, actually, on the surface. And we think that goes down to very, very small sizes. But we don't know exactly how this dust is put together and how it interacts. And that's really important. Oh yeah, Becky's just put up a beautiful picture here showing that, it kind of pulls. Some of the areas of the nucleus is very rugged. Some of it's very smooth, where obviously the dust is pulled and it's much deeper. We can even see dust dunes on the surface, or ripples. Now, that may be caused by surface flows of gas over the surface. It may be just the dust moving slowly under self-gravity into kind of lower regions, although you have to be careful when you look at a comet nucleus, because there's not much of a difference between a high region and a low region. But we don't even know really how deep that dust is, though it certainly gives the impression that it's probably at least a meter or two thick on the surface. But what makes that area different from the other areas, we don't know. This is what Philae is going to tell us. It's going to give us this really up-close measurement of the surface properties of the nucleus. How fragile is it? How porous is it? How is it put together? At the same time, of course, it's going to be making many other important measurements. Again, we're talking about this mass spectrograph on Rosetta, making measurements of the gas from 10 kilometers away. Philae has an incredibly sensitive mass spectrograph. Actually, and it was built and is operated by a team from the Open University in the UK. And that is going to give us the true measurements of material just as it's released. We know that there's active regions around the Philae landing region, so it's going to get the really fresh stuff just as it's released from the surface, just as it's released from this primordial ice that's been basically sitting there for 4.5 billion years. And when we put all this together, one thing we hope to get out of it is, in terms of composition, what was the material that came and helped build the other planets of the solar system, such as the Earth? Because comets are just the leftover building blocks of the solar system from 4.5 billion years ago. In fact, they're much more like the stuff that went into building the planets. If we look at asteroids, we know most asteroids have been altered. They're close to the sun. They've lost a lot of their lighter elements. But the comets are showing us what really went into forming our solar system. So compositionally, it's going to be important. Also, but one other thing, one incredibly exciting thing that the lander will do is that we hope it's going to give us our first real look in the interior of a comet, something we haven't done before. Because combined with the Rosetta orbiter, we have an experiment on board called CONSERT, and CONSERT is going to basically perform radar tomography of the interior of the comet. So Rosetta will send out these radar pulses through the nucleus to the lander. The lander will receive them, and then send them back. And what we'll have is these radar pulses going through the nucleus. And from that, we should have some idea of the interior structure of the nucleus, and that's going to give us clues about not only what is the nucleus made of, what went into building these comets 4.5 billion years ago, but how were they put together. And we have ideas, but we have no measurements, and this will be the first measurement.
This is, of course, where the name Rosetta comes from the Rosetta Stone that is said to contain the secrets of the birth of civilization in some senses. So this will be the birth of the birth of the solar.
That's right. That's right, and of course the Rosetta Stone was the opening to our door of the ancient world because it contains the same words in both ancient Greek and Egyptian hieroglyphs. So it acted as the bridge to the understanding the ancient Egyptian civilizations. But to actually, it's interesting enough, to actually get the full translation of these pictograms that the Egyptians wrote in, there was an extra clue that was needed, and that came from an ancient obelisk on the island of Philae, which is where the name of the lander comes from. So you have to put the Rosetta Stone and the obelisk on Philae together to get the complete picture of what this ancient civilization was like. And we think that's what we're going to do, or we hope that's what we'll be able to do with Rosetta and its lander as well.
Excellent. Now, one more question has come in about the lander. So Matthew Withers has asked, how are we sure the harpoon and screws will hold the lander, and if the surface sublimates off, surely that will cause the lander to become loose? Well, referring to the first part about how we sure they'll actually hold the lander, in some senses, we're not sure, right, Alan?
That's right. It's the best system that could be designed by the finest engineers in the space program. But one of the things Philae is going to do is going to tell us what the surface of a comet is like. And if you don't know what the surface is going to be like, how do you design a system that will keep a lander on the surface? You use harpoons, you use screws, you use a thruster. You also design it. This is an important thing with these images. The images that Becky showed earlier of the landing site. It looks quite rugged, and in fact that's because all of the surface of the nucleus is fairly interesting, as you might say. Now the lander itself is also designed so that if it lands, it doesn't need to land horizontal. It can land anywhere up to 30 degrees off horizontal, and it will still be fine. It's designed that way. Even probably up beyond that, although the engineers won't guarantee it, they'll say that it'll still. It has a good chance of being okay. So this is the problem. As you say, Chris, we don't know it'll work, but nobody could think of any other way apart from perhaps attaching big sticky pads. Now, the other thing, though, is that the second question was, won't it just come down and it'll be blown off again? Well, the actual gas pressure over most of the surface is very low. And certainly where Philae is landing at the moment, although there is activity there, it can be, the Rosetta has detected activity from some small vents in the landing region. It's not powerful enough to stop this lander coming down because, although remember it's very low weight, it still has inertia. So it will come down, it will land, at about 1 meter per second, and it will land okay. Now, what happens later on in the mission? Well, who knows? We've never done this before, and that's the whole point of going to a comet. You find out what it's like. But if anything could be a success, Philae will be. Rosetta already is, and all I'm waiting for are the first data and the first images from the surface. It's going to be fantastic.
So Becky, this is one of the big missions that are currently around. It's obviously one of the European Space Agency's flagship missions. It's got to be one of the most exciting missions around at the moment. So how much are you looking forward to the 12th of November?
So looking forward to it. I've got like a countdown on my iPod and everything. It's not just the 12th of November though, because I know that the mission is, it's going to land then, but that's not going to be the most exciting point, the landing. Yes, it will be great when it's down and it's on the comet, but the most exciting point is going to be that first discovery, that first thing that we find out when we're on that surface. And that could be weeks, it could be months, we just don't know. And obviously Rosetta is going to stay with the comet till, I think it's like December 2015, and so we're going to have more and more information all the way through till then. So I'm excited for the whole next year.
It's going to be a ride. Now we should say, of course, that Rosetta and Philae and Churyamov-Gerasimenko are not the only stories that have been in the news this month. So there's also been a couple of others. We've got a few minutes left to cover them. So it's not even the only comet. So there was, of course, a comet in the news because it whizzed by Mars, getting incredibly close to Mars. Yeah, there's an image up there of. This was Comet C2013A1 Siding Spring, to give it its full title. I think I got that right. Mm-hmm. And this went past Mars last week, I believe. And this is a photo captured from one of the rovers, I believe.
Yeah, I think it's Opportunity that captured this on Mars, which is really quite cool. I think it's the first comet we've ever observed from the surface of another planet.
Is that right, Alan? Does that sound right? That the first one we've seen from another planet?
I think that's right. I mean, a spacecraft throughout the solar system have observed comets over time, even though it hasn't been their primary mission. But I think that's right. I think this is the first comet, as far as I know, observed from the surface of another planet, and that's pretty cool.
It is. It's that, for those who can't see it, is that fuzzy blob Becky was just highlighting right in the middle. The rest of it is either stars or cosmic rays hidden the detector. I guess we've got time for one other story, one other news note. So I guess, is the sunspot quite fun, Becky? You had a nice big sunspot.
Yeah, I love this sunspot. Sure. I haven't managed to see it through any sunglasses or anything yet, but it's absolutely fantastic. It's given off an X solar flare the other day as well that caused some amazing aurora. It is absolutely huge. It's the size of Jupiter, and I mean, it's one of the biggest ones we've seen in a long time. Because the sun's been quite quiet, but this is fantastic.
And of course, it's near the equator, so you never know. It might end up sending some stuff our way and give us some nice aurora, and hopefully not too many problems.
Yeah.
When it sends stuff our way.
At us.
But yeah, that's a pretty impressive sunspot. So if you do have the ability to go out and look at the sun safely, you can project it through. Again, if you know what you're doing, you can project it through a pair of binoculars. Just do not look through the binoculars at the sun. Project it through binoculars onto a shaded piece of card, and you might get a nice image, and it should be rather easy to see. So, Alan, you're up there on top of a mountain. Do you think you're going to have time to look at look at the sunspot at all?
Well, the problem is, if you shouldn't look at the sun with binoculars, you certainly shouldn't use an 8.2 meter telescope to do so. So I'm not sure how I'm going to get at it, because I don't even want to look at the sun. The sun's out here, but I don't even use my sunglasses, because I mean even that's dangerous. So I think I'll try to look at it at sunset, because we get a good view of the sunset over the Pacific Ocean from here. I'll see if I can see it near sunset, but
it should be quite a sight. I guess that's probably all we've got time for. So is any final thoughts from either of you before we?
I have the ISS is only visible for the next couple of days, and then it disappears until December. So if anyone wants to catch it, it's going to be really bright tomorrow evening, 6:30. So when you're back from work, check it out.
So that's visible from the UK. Of course, the ISS is still there. It's not going to fall out.
Yes, it's going to disappear from UK, guys.
Excellent. And yeah, so go out and check that out if you can. Alan, I wish you luck with your observing run, finding out everything about Rosetta if you can. How long are you there for?
I'm not working tonight. I'm just preparing the observations. Then I'll be working tomorrow night for 3 nights observing the comet. Actually, it's very nice for me that the comet sets by midnight, so I only have to work half nights, which suits me fine.
So you go to Chile, you go up a mountain, you go observing, and you don't have to go to bed stupidly late. Very, very jealous of that. On that note, I think we'd probably better end. We've had a half hour. So thanks to everyone who's been watching. I hope it's been fun. I've had fun chatting to Alan Fitzsimmons from Chile, although from Belfast is where he works, but he's currently in Chile, and Becky Smethurst. So thanks, guys, for joining us, and we'll be back in about a month. Keep your eyes posted for the next link.